In Excel, you can I think recording started a little late. I cannot help it, but okay. So this is how you can calculate the effects of AB, ABC, all the interactions. And these are the plots, interaction plots. We have seen this all in Minitab, but I just wanted to run through this. And now uh, you can use the regression table, a regression equation for the predicted response. We have discussed about regression equation also yesterday. This slide shows how to convert coded values into uncoded or vice versa. That's an easy one. You can just check that. That's elementary. And you can make an Excel table to make a prediction, Excel calculator kind of a thing. Now, this is the part which I have shown in Minitab yesterday. Now, there are certain terms that I wanted to explain here on slide number 49. You will see the analysis of variance output, which we didn't go through. And you can see that wherever the p-value is low, wherever the p-value is less than 0.05, if you assume alpha risk of 0.05 or 95% confidence level, wherever you see a low p-value, that is significant. So, and below that, you also see the R square values, R square adjusted values. So here it is that here is the table. I think it should be like this. The red circles are not proper. Yeah, they should be here actually only for the zero terms. I'm just adjusting this because you should not get an. I don't know what the PDF is showing, but wherever you see a low p-value, that is significant. Sorry, it's not changing. Okay. So below that, you can see the values of, I just want to show you these values. The S is the standard deviation of the residuals. What are residuals? The observed values minus the predicted values, because you can make the predictions using the prediction equation. So the difference between those values, observed minus predicted, is and that standard deviation of that is S. It should be as low as possible. The lower the value, the lower is the difference between the observed and predicted values. That means your model is good. R square shows how good is the model. Yesterday, I think in the previous session on correlation regression, you discussed about R square, but this is the same value, but it applies to the whole this analysis of variance table. So this tells me how much of the variation total is explained by the model that I selected. So it's about 77%. So variation explained by the model is about 77%. A modified value R square adjusted is also shown, which actually ignores some insignificant effects. So it's a modified value, and that is 66.89. And then there is a prediction R square. That means if you want to predict a new interim value, prediction for a new interim value, it will be as good as about 48%. So the prediction power is not as good as we would like to have it. I would also explain on the next slide R square adjusted values. R square adjusted is the percentage of response variable variation that is explained by its relationship with one or more predictor variables adjusted for the number of predictors in the model. The adjustment is important because R square for any model will always increase when new term is added. A model with more terms can seem to have a better fit because it has got more terms. However, some increase in R square might be because of the chance alone. So note, when R square adjusted is negative, Minitab will make it, or most software will make it to 0. So in this case, the R square adjusted value is 48.79, and the formula is shown here, 1 minus mean square error upon total variance. And that can be calculated as 66.89. You can check the calculation later. This is anyway calculated by Minitab. So, and on the right side, you will see total sum of squares, total degrees of freedom 23, error degrees of freedom 16, 23 minus 7, as you will remember, we just looked at that. So this is about the R square value and R square predicted value. I think this is R square predicted. So this is R square predicted value is 48 something. Difference between R square predicted and R square adjusted should be less than 20%. Some softwares give this guidance that the difference between R square predicted and R square adjusted should be less than 20%. So which is so here the difference is about 18%. So it's a predictive ability of the model R square predicted. So we have seen the reducing the model and we have seen the backward or omitting the terms. Now we have not discussed this residuals basically. So residuals, each residual represents, there are total 24 readings, 24 data points. So these are observed data points, and then there are 24 predicted values. So there will be 24 differences between the observed and predicted values, which are called errors or residuals. So these residuals are plotted on a normal probability plot. This might not be discussed earlier, but these points should actually follow a straight line if you want to check whether the residuals are normally distributed, which is one of the assumptions of the analysis of variance. So this should be approximately distributed nearly around the straight line that you see here. So residuals can be considered normally distributed when the points are close to the straight line. Now, this is a visual judgment, and in this case, it's not a major concern, but some points seem to be a little away, but not a major concern. And we have seen the main effect plots, and yeah, we have seen the contour plots. We have also seen the surface plot. We have seen the response optimization. Yeah. Now, uh, you have this. Just a minute. Take this up so that you can see. Yeah, designing a 2 to the power 2 experiment, I think we have already seen. And the regression equation also we have seen. This slide is probably not required over here. Yeah, I think this only talks about how to denote the experiment. So when the factor is at low level, so I'll just use, let us say, whiteboard or maybe a blank PowerPoint. So what I'm talking about is, let us say you got two factors, A and B, and let us say I have a 2 to the power 2 design. So this is minus 1 plus 1 plus 1, and this will be minus 1 plus 1 minus 1 plus 1 coded values. Now, this can be represented, so denoted as. So I'll make a column for how it is denoted. When the factor is at low level, it is considered as absent, and factor A is represented by a small letter A, and factor B is represented by small letter B. So this will be, since it is both are at low levels, I will consider this as absent and raise it to the power 0. So I'll call it A to the power 0 and B to the power 0, or it can be considered as 1. The second row will be A to the power 1, B to the power 0, which means A. Then you got A to the power 0, B to the power 1, which is B. And then you got both at 1, A raised to 1, B raised to 1, which is AB. Now you can represent this with a graphical in a graphical manner. So you'll say, okay, this is my factor A and this is my factor B. So this is my both at low level. So this is 1. Then this is at A at 1 level and B at 0 level. So this is A, this is B, and this corner is AB. That's why these are called corner points. If you remember Minitab calls this as corner point. If you have a third factor, you will have a cube plot, and that is what it is usually called. So I'll just show you a cube plot also. So if you have a third factor, A, B, C, so let us say this is A, Sorry. So this is factor A, then you got factor B, and then you got factor C, which will be something like this. So this will be the all at low levels. So this is factor C. So all ABC at low level, but that means this is 1. This corner, the extreme corner is ABC, all factors at high levels. This will be A, this will be C at high levels, so C. Then this will be B, and then this will be B at plus and C at plus, so this will be probably BC. This will be A at plus and C at plus, so this is EC, etc. So you can name all the columns, but it's a cube plot. So Minitab could generate the cube plot also. I'm just opening the file that we used yesterday and showing you the cube plot in Minitab. So I'll just say stat DOE. I have just opened the same file, factorial and cube plot. So, and this is fitted means, so predicted means will be shown here. So tool life. So it will be something like this. So this is how it is. So you got cutting speed on the x-axis, then you got coolant on the y-axis, and then you got rake angle on the third axis. And these are the mean values at each corner. Now, the beauty of this is that you can calculate the effect of each factor from this graph also. How you will do that? If I copy this, and want to show you, so I'm just copying this and pasting it on a blank PowerPoint. Yes. So this was the one. So now what you can do here is, let us say you want to find out the effect of cutting speed. Now cutting speed is at high level for all these points. So if you find out average of this will be average of cutting speed at high, and the left side points will be all at cutting speed low. So average of this high points and average of low point, difference between this will give you the effect of cutting speed. If you want to calculate the effect of if you want to calculate the effect of the other factor, any other factor, you could choose the other planes, for example. So suppose you want to find out the effect of coolant. Now coolant is at low level, high level for all these points and low level for all these points. Coolant A. So this is coolant B and this is coolant A. So the difference between these averages will show you the effect. So this graph you can use to calculate the effects also. That is just for your reference. I think with that, we will move on to the fractional factorial designs, which is the topic for the day. Here you can see the cube plot and other things and how it is denoted. Yesterday, somebody had asked about the management applications of this. Finance, I don't think there are too many which I found. Kindly mute yourself. Mr. Aniruddha Ghosh, can you mute yourself? And this instruction is for everyone. If you have a question, please speak, but otherwise keep yourself muted. Okay, so I just want to show you a page here, and I have pasted the link in the chat box. This is a LinkedIn article by Mr. Murlidhar Anantamurthy. It talks about business experimentation, harnessing the power of DOE in business and management. So I suggest that you can, those who have want to look at this, they can look at this article and get some insights into this one. This is a LinkedIn article. So I believe you can easily access. I have given the link in the chat box right in the beginning of the session. All right. With that, we go to fractional factorial designs. Degrees of freedom we have already discussed. Now we are going to do that again. So let us move to fractional factorial designs. Now I'm going to use Microsoft Excel. If you wish to follow me, you can. Otherwise, it may be a little fast for you, but observe what I am doing in the fractional factor, this Microsoft Excel to explain what is a fractional factorial design. Now let us say you have a 2 to the power 2 design and it has got two factors, A and B, and a single replicate of this will have low, low, high, high, and A also low, high, low, high. So this is a design that you have in a single replicate of the 2 to the power 2 design. Now, if I add a column AB here, now I can say multiply the two column signs to get the AB sign. So I have this AB sign also. Now this was the design that was a 2 to the power 2 design. So I'll call this 2 raised to 2 design. 2 to the power 2 design. As you know, the level to the power factor gives you the number of runs in a design. Now, suppose I am ready to sacrifice the interaction EB. In that case, what happens is I can use this column to set the factor C, which I'll say C is equal to AB. C is equal to AB. That means I use this. So this is C high. So I'll just write with a pen here. So if I use this column, so this is C high, C low, C low, and C high. So if I use this column to set a level of factor C, that is the third factor in this design instead of two factors only. In that case, the design becomes like this. Now, can I do this? Because it looks fine. I mean, you can also calculate the effect of C. What is the problem? The problem is very simple. Now, if I put it is obvious that this C and AB are in the same column. So I will say that I cannot distinguish between C and AB. So C and AB cannot be separated or cannot be I'll say effects cannot be separated. Now, this phenomena is called confounding of effects. That means you cannot distinguish between the effects. Now, let us start with another design, a three-factor design. So I will say now I'll do a 2 to the power 3 design. Now that means I got A, B, and C. So I'll say A, B, and C. Obviously, 2 to the power 3 means there are 8 runs. Half of them will be -1 for C. Then half of this 4 -1 runs will be -1 B and then +1 for B again -1 two times. So I am splitting into half of, and then for A, I will again split the negative 2 runs into -1 +1, -1 +1, -1 +1, and -1 +1. So this is the design that I get, and it's a standard order of a 2 to the power 3 design. So this is treatment first. So there are totally 8 treatments in this. Now I can also create the columns AB, interaction column BC, and AC. or let us say, yeah, okay. And also ABC, ABC. So I have created these extra columns and I can now add the signs to this. So AB sign will be A star B. BC sign will be B star C, B into C. AC sign will be A into C, A star C. And ABC will be multiplication of the three. So I can say B into AC, B into AC or any. And I copy this to get signs of all the main effects as well as interactions. Now, it is said by experts that as you increase the number of factors in the interactions, the magnitude of the interactions usually becomes smaller and smaller. So in that sense, it's called sparsity, yeah, sparity of effect, not sparsity. So it's called sparity of effect, I suppose. I'll just say sparity of effects. Yeah, it is sparsity of effects, not sparity. Sparsity of effects principle. So the sparsity of effects principle states that in a statistical experiment, usually only small number of factors, typically main effects and low order interactions, significantly impact the outcome, while most other factors have no or little or no effect. Essentially, most systems are dominated by few key effects rather than complex interplay of many factors. That means complex interactions are uh, generally not high and not significant. If I use this idea, that means ABC is likely to be a small effect. So if I decide to ignore ABC, that means I can use this ABC column for one of the for an additional factor D is equal to ABC. But if I just push that, then it is going to be I mean all 8 runs I will have to do. So I select. So I use a filter command here. Let us say I do a filtering and I select only the plus ABC runs. So I am not interested in ABC interaction anymore. So let us say I select only ABC is equal to 1. Now, if you want to calculate the effect of ABC from this design, you can see that since you selected only ABC is equal to plus 1, the number of runs have reduced or the number of treatments have reduced from 8 to 4. That is, we have reduced from full factorial to a half fractional design. So this is half fraction of 2 to the power 3 design. So this is called half fraction means 2 to the power 3 divided by 2. So you can say 2 to the power 3 minus 1. So it is usually written as 2 to the power 3 minus 1. So it is half fraction of the 2 to the power 3 design. Now here, the interesting part is, can you ever calculate ABC effect? The answer is no, because you need average at high level minus average at low level, but there are no low level runs. So you cannot ever calculate ABC from this design. But now let us see whether you can calculate A. I will just mark this numbers here with, let us say I will use conditional formatting and color scales. So let us say plus 1 runs are marked with red. You know, again, there is someone talking. So may I request you to mute yourself, please? Mr. Sandeep Bhanot, you're not muted. Can you mute yourself? Or do you want me to mute yourself? I'll say mute all. So I'm muting all of you except myself. You can unmute yourself when you want to speak. Yeah. Coming back to this half fraction design, you can see that can you calculate A? Yeah, you can, because you have two plus runs and two, that means two high level runs and two low level runs. B, can you calculate? Yes, there are two high level, two low level. C, yes, two high level, two low level. AB, yes, two high level, two low level. BC, yes. AC, yes. But now, if you observe the sequence of signs, there is something that has happened in between. Now, if you see here, AB and BC, sorry, C and AB, the sequence of sign is identical. So the if I call this as treatment number 1, treatment number 2, treatment number 3, and treatment number 4. So calculation of C will be average of these two runs minus average of the low level runs. But AB also is the same calculation. That means C is cannot be distinguished separately with respect to AB because the same runs will come in the calculation. I would say C is effect of C is confounded with AB, that is two factor interaction of AB. Now look at the other columns, B versus AC. So if you look at B versus AC, the signs are again same, green, red. So B signs are synonymous or same as AC. I would say B is confounded with AC, or I cannot distinguish between B and AC. Similarly, A and BC, the signs are same. So I would also say A is confounded with BC. And ABC, of course, we have already sacrificed because we decided not to get the effect of ABC with the sparsity of effects principle. So I tried to, what is the benefit that you got? The efforts are reduced to half. It is half fraction. What did you lose? You lose the discriminating power in the design. So you have confounding of the main effects with two factor interactions. So I would say here that main effects are confounded with two factor interactions, two factor interactions. Now I can extend this idea to further. Let us say I add fourth factor here. So I make it ABCD now. A, B, C, D, and I can go on increasing. And it will become more and more complicated because I will have to omit ABCD effects and ABC effects to get. So let us do one more exercise of this and see what confounding you get. So since now this is 2 to the power 4 design, there will be 16 runs. So half of this will be 8, which will be low here. I will just copy this. And then you got, so I think 1, 2, 3, 4, 5, 6, 7, 8. So this is the D. Now, out of this negative 8 runs, C will have 4 negative and 4 positive. And this pattern will be repeating for the next 8 runs. That is for C. B will have 2 minus 1, 1, 1, minus 1, minus 1, 1, 1. And this pattern will be same for the remaining runs. And here you got A, which again will be minus 1, 1, minus 1, 1. And this pattern is going to repeat all throughout. So I got the table for ABCD design, and I will have to create the interaction columns. I generally don't do the 2 to the power 4 design, but I think let us do this. So you got AB, you got AC, you got AD, you got BC, you got BD, then you got CD, right? So there are 6 two-factor interactions, and then you got ABC. Okay, there it will be a complicated. So I think let us not do this. You can sort out this table later because it will take a lot of time, and unfortunately we don't have that much time. I can extend this table. So if I list out just the interactions, I won't may not create the table full. So ABC will be there, then CD will be there, then ABD will be there, etc. So you will have again the number of interactions that you get can be calculated by the formula. There is a formula that you can see. So the number of interactions, I'll just show the formula. The number of interactions of R factors taken at a time, or K factors, let us say, not R factors, K factors, K factors out of. So that is given by, and let us say that the total number of factors is, we will have to consider F 2 to the power L to the power F. So F is the number of factors. So total factors is F, C, K, K taken at a time. So here you got 4 factors. And if you want to calculate the interactions of 2 factors at a time, it will be 4C2. So that will be factorial n, that is factorial 4, divided by factorial 2 into factorial 4 minus 2 again. And this gives me 4 into 3 into factorial 2 divided by factorial 2, which gets cancelled, and into factorial 2 again. So this is 12 upon 2, that is 6. You could also see how many 3-factor interactions will be there, 4C3, and that is equal to factorial 4 upon factorial 3 into factorial 1. So this is 4 into factorial 3 divided by factorial 3. So I think that will be 4 interactions. And obviously, if you take all 4 at a time, it will be 4C4, and that will be 1, because this is factorial 4 upon factorial 4 into factorial 0. Factorial 0 is 1, so this is 1. So this is the way you can calculate the number of interactions that can be present. Now I'll go back to the material and show you some things, some slides. Why are we doing all these things? How many runs are required for different experiments? Okay, let us say, as you know, the number of runs is shown by L to the power F. So 2 factors, 2 levels, 4 runs. 3 factors, 2 levels, 8 runs. 4 factors, 2 levels, 16. So each additional factor doubles the number of runs, that is in geometric proportion. So 4, 8, 5 factors, 32, 6 factors, 64, 7 factors, 128, 8 factors, 256, 9 factors, 512, 10 factors, 1024. So as you see, it rapidly increases, and the experiment becomes expensive as well as unmanageable, because you'll have to collect data on so many number of runs. So it becomes unmanageable. If you add one more level to the factors, then it will be even more. 2 factors, 3 levels will be 9 runs. 2 to the power 3, 3 to the power 2. 3 to the power 3 is 27. 3 to the power 4 is 81. So you can see how rapidly it increases. So because of this rapid increasing number of runs, uh, statisticians have considered fractional factorial designs, which I just introduced on Excel to some extent. But now let us go into few details of that. Fortunately, statisticians have created efficient designs to reduce the number of runs. This has to be used very smartly, and we will see how to use our smartness to select the designs. Number of effects in an experiment I just show you. KCR is, and that is if you have five factors and in a 2 to the power 5 experiment, number of two factor interactions is 5C2, which is 10. So you can calculate the number of interactions for a given number of factors at a time. So now number of effects in an experiment, let us consider 2 to the power 5 design. We can calculate 5 main effects, 10 two-factor interactions, 10 three-factor interactions, 5 four-factor interactions. This you can calculate with KCR or whatever, and one five-factor interaction. So if you take a total of this 5 plus 10 plus 10 plus 5 plus 1, that is equal to 15, 25, 30, and 31. So total 31 effects are there in this design. So the number of runs is 32 and the degrees of freedom available is 31. And since each of this has got two levels, the degrees of freedom required will be obviously, it will be obviously, yeah, 5 main effects will be 5 degrees of freedom. This is 10 degrees of freedom. So each, this will be total 31 degrees of freedom required. So you got 31 available and 31 required. So nothing left for the error term. Now that is the peculiarity of every full factorial design. If you want to calculate every effect that is available in the design, then you lose the degrees of freedom and there is nothing left in the error term. Of course, you can reduce the um, yeah, you can reduce the analysis. I mean, we can reduce the number of terms by selecting smartly, like we did in Minitab yesterday. But still, there is a better way of doing it by design. So you can see here, based on the principle of sparsity of effect, these effects are usually small. Thus, we have only 15 effects to estimate. So sparsity of effect says that higher order interactions may be small. So three factor interactions 10, five four factor interactions and one five factor interactions are likely to be small. So if you are discarding this, you have only 5 main effects and 10 two-factor interactions. So there are only 15 effects to be evaluated. And if you want to evaluate 15 effects, you can actually do that in half fraction. So that is what you can see, that half fraction of this will have 16 runs, and you will have to do it, of course, smartly. A, B, C, D, E positive or A, B, C, D, E negative, one of these columns you will have to select. So sparsity of effect principles I have already told, and that is also there. I have shown in you on internet. So this is the basis of this fractional factorial designs. So what are fractional factorial experiments? Statisticians have designed fractional factorial experiments to reduce the number of runs or trials. Only selected treatment combinations are tried instead of all. In fractional factorial designs, we compromise on some loss of information to save cost and effort, which is the confounding. So the left side graph shows the left side graph shows a full factorial design for three factors, 2 to the power 3 design. While as if you select only ABC plus one runs, probably you will select these four corners only. So this is A, this is B, this is C and ABC. So you will select only these four runs if you are doing a half fraction of the or 2 to the power 3 minus 1. I have shown this on Excel some time back, but this is a graphical representation of this half fraction. Now, this is what I showed on Excel for a three factor. So these are the runs if you select the ABC plus one runs only. So the runs that you select here will be A plus, that is A, then B, then AB you are ignoring C and ABC, A, B, C and ABC. This is what you have is the principal fraction if you select ABC is equal to plus one. You could also select ABC minus one runs. So that is the second fraction or alternate fraction that you can use. In that case, you will be using the other four corners. That is 1, AB, AC, and BC. These are the four runs that you will be selecting, the remaining four corners. So that's how there is a principal fraction and then there is a secondary fraction, you can say. And minute I will ask you which fraction you want to select. Generally, the principal will be plus one, ABC plus one. So if I want to create this design in Minitab, I just want to show you here. I create stat. I continue in the same file. So I go to stat, DOE, factorial, create factorial design, two-level factorial default generators. Number of factors I choose as 3. And now if you click on the display available designs, you can see for 3 factors, there are 2 designs available. If you have half fraction that is with 4 runs, it's a resolution 3. I'll talk about the resolution in a short while. And 8 runs will be a full. We are selecting a half fraction here with 4 runs. So I select in the designs, I'll select half fraction. I will only say number of replicates, corner point, single replicate, block 1. Factors, I will just keep it as ABC. And now I'll say OK. When I say OK, it will create that design. So the design is created the same as what we have probably seen in the in Microsoft Excel. So if I list this design in standard order, it's better. I can match it with the DOE display design and standard order. So the standard order is like this, ABC. You can see that, okay, it has considered B as -1, -1. Okay, this is the design that it has created. Let us see whether it matches with our design here. I'll just, or maybe even here I can do that. No, here I can't do this. I will have to do this on Excel probably. Okay, I'm just listing the design here. So you can say you can compare with the ABC plus one designs. That is -1, -1, -1. So let us see whether it has created that one. Oh, it has. Good. I'll just list it below so that I can filter and check. Yeah, -1, -1, -1. It hasn't selected. I think it has selected other fraction probably. So let me see which fraction it has selected. So stat, DOE, factorial, create factorial design, 3, and designs. Yes, half fraction. Yeah, I think in the factors, yes. In the options, I think you have to select the fraction. Use principal fraction, use fraction number. I don't want to randomize runs. Or maybe fraction number 1, I will just say. Let us see what it has created. The earlier one was, yeah, I is equal to plus ABC. So that means, yeah, ABC plus 1 were selected. And alias means confounding structure. So A is confounded with BC, B is confounded with AC, and C is confounded with AB. So that is there. So this is the confounding structure Minitab has shown. And even in the second case, it is I is equal to minus ABC. So I think this has selected minus ABC. Earlier it had selected plus ABC. So if I go and select the other fraction, maybe 2, yeah, the fraction 2 is I is equal to plus ABC apparently. So first one is minus, and yeah, here C is equal to AB and here C is equal to minus AB. This is called design generator, which that means you can generate it from the lower level design also. If you select it from the higher level, then it is identity column. I is called the identity column, and that is plus ABC means you have selected runs related to plus ABC. So here, as you have seen, this confounding structure, I don't know why this is not matching. Did I make a, maybe I have made a mistake here probably. I don't know whether I made a mistake here. Yeah, -1, -1, -1, +1, -1, -1. Yeah, this is okay. So have I calculated ABC column incorrectly? Let me do it once again. A star B star C. And if I select +1, yeah, we should have, yeah, now it is, I think I made a mistake in the ABC column calculation. That's why it was not matching. So now you can see 1 -1 -1. So 1 -1 -1. So this will now match. Now, as you know, A is confounded with BC, B is confounded with AC, and C is confounded with AB because the sign sequence is identical in those columns. So that means this design is, if I if I indicate this design or show this design, so I will say main effects confounded with two-factor interactions, and namely A is confounded with BC, B is confounded with AC, and C is confounded with AB. So this is the confounding that has happened. And ABC I cannot calculate. Now such a design is called a resolution 3 design. Now let us understand what are the resolution codes. The resolution code you can use. Now I'll show you a table here for the resolution codes. Yeah, here is the description of the resolution codes. So you can have resolution 5 designs, and 5 designs means no main effects or two-factor interactions are confounded or aliased. Confounding is also called aliasing. Alias means same name, I mean two different names for the same quantity. That is aliasing. So no main effects or two-factor interactions are aliased with any other main effects or two-factor interactions, but two-factor interactions are aliased with three-factor interactions. And then you got resolution 4, resolution 3. The simplest and the best way to understand this is I will just stop sharing for a moment and explain this to you with 5 fingers. So let us say if you are able to see my hand here, there are 5 fingers. Consider that the number of fingers represent the resolution of the design. So if I say these are 5 fingers, then the combinations of this will be 1 finger and 4 fingers. That means main effect. 1 finger represents the main effect and 4 fingers represent four-factor interactions. So main effects are allied with four-factor interactions. That is one confounding structure in this 5 finger design or resolution 5 design. But the other possible combination is 2 and 3. That means two-factor interactions are allied with three-factor interactions. So that is what is described in that table. Now, if you consider resolution 3, that means I have only 3 fingers. So the resolution 3 design is represented by 3 fingers. What are the combinations? 1 finger and 2 fingers. That means main effects, which is represented by a single finger, are confounded with two-factor interactions. So that is what is resolution 3 design. Resolution 3 design doesn't give you any interactions, to be honest with you, because two-factor interactions are the lowest possible interactions. But now consider 4 fingers as a last possibility. What are the possible combinations? 1 and 3. That means main effects are confounded with three-factor interactions. and then 2 and 2. That means some two-factor interactions are confounded with some other two-factor interactions. So now if you look at the table, I'll again share this table with you. So now you can see for resolution code 5, no main effects or two-factor interactions are allied with any other main effects or two-factor interactions. But two-factor interactions are allied with three-factor. 2 plus 3 is 5. And 1 plus 4 is also 5. So main effects are allied with four-factor interactions. What is the benefit of this? The four-factor interactions are small and three-factor interactions are also expected to be small. So you get a good information about main effects and two-factor interactions into this. Confounding is there, but it's not going to bother you much based on the sparsity of effects principle. Now, if you see resolution code 4 design, the combinations are 1 and 3. So if I write the confounding on the right side, so main effects are confounded with four-factor interactions and two-factor interactions are confounded with three-factor interactions in resolution 4 design. I mean resolution 5 design. Here it is 1 confounded with 3 and two-factor interactions confounded with some other two-factor interactions. So 2 plus 2 is 4, 1 plus 3 is also 4. And now in the resolution code 3, the main effects are confounded with two-factor interactions. And that's it. That's the only possible combination. So this is what you mean by the resolution. And why the resolution code 3 is shown in red is that main effects are allied with two-factor interactions. That means you don't get any interactions in resolution code 3 designs, to be honest with you. So resolution code 3 designs, why do they exist? Those are used for screening purposes. I'll talk about it now in the table. So far, is there any question from the participants? I have covered a lot, so maybe there is a question. We got 172 participants, so if there is a question, I'll take. Otherwise, I'll proceed and take the question later. Any interim question? No questions. Okay, thank you. So we have seen the resolution codes, and I have shown you this also, the three finger, four finger. So this is resolution 4 design, and this is resolution 5 design. I have explained this actually. And now look at the table that is reproduced from Minitab now. I'll just animate this a little bit. Give me a minute. I don't want to play the narrations. Okay, following table shows the number of runs in various designs according to their resolution code. The top row shows number of factors and the left column shows the number of runs. So this is the number of factors, the top row, and this is the number of runs. So 2 factor, 3 factor, 4 factor, etc. Now, the green designs are resolution 5 or higher order, higher resolution designs. And they are all shown in green color. So these are either full factorial designs or resolution code 5 and above designs, the green ones. The resolution code red designs are resolution 3 designs and resolution 4 designs are shown in yellow color because they are resolution code 4 designs and you can use it sometimes. So if you know something technically that these interactions are unlikely, these are likely, then you can choose the resolution code 3 and appropriately do that. I think I need to uncheck the use timings here. So these are the green ones. Then you got the red ones, which are resolution code 3, and the yellow ones are resolution code 4. For example, if a team has shortlisted 9 factors, the screening design of resolution code 3 will have 16 runs. So imagine that somebody is starting with the 9 factor design. The 9 factors, how many full factorial runs will be required? 2 to the power 9. And that is a very high number of runs. We have seen that. I think that will be 256, I suppose, or maybe even more, 528. So that will have so many number of runs. But if you choose only 128 out of this, then that becomes a resolution 6 design. But if you choose the red design, you need only 16 runs. And out of this, by doing this 16 runs, you can discard some of the factors which may not be significant. So let us say you find five significant factors out of nine. Then you go to the another column with five factors for the second design and now choose a resolution code 5 design, another 16 runs. So you have done first 16 runs with nine factors, discarded four factors because they were not significant. And now for the remaining five factors, you choose a resolution code 5 design wherein you get reasonably good information uh, about the interactions, two factor interactions, and then you can do this design. So 16 plus 16, 32 number of runs, you are quite close to the final solution. Of course, you are taking some amount of risk because you are ignoring some of the confoundings. So you will have to be clear. You will have to have clear understanding of the R square values that you get, the R square adjusted values that you get, the insignificant factors. So you should be careful about interpretation of the designs, ANOVA tables, and all these things. Then you can use this table judiciously. Again, I'll ask you: are there any questions at this stage again from any of you? I have explained you the phenomena of confounding and the resolution codes in the design. Now I'll show you an example of a fractional factorial design in Minitab, analysis of that, and few more concepts that I did not discuss yesterday. Yes, please. Yes.
Hello.
Yes, please.
Yeah, good evening, sir.
Good evening.
Sir, many times we use the combination of the polymers
Can you
in
speak a
ratio.
little louder, please?
Yeah, many times we use combination of the polymers for the research
Yes.
purpose in ratios like
Okay.
50 to 50,
When you are
7 to
using the
30.
polymers, is the total proportion of polymer elements is supposed to be 100% or one?
So many times we use 1:1, 1:2, or 3:2 like this. So how to
Well,
select in such case the factors?
I think, suppose in the polymers, if you want to increase the proportion of one element, you'll have to reduce proportion of some of the other elements. Is that correct?
No, sir. Every time it is not 100%. Sometimes 1:1 or 1:2 like this.
No, no. Don't talk about the ratios right now. Talk about the
Uh,
basic elements in the polymers.
yeah,
Give
if
me
we
an
use
example.
HPMC and ethyl cellulose,
Sorry.
HPMC and ethyl cellulose, HPMC and EC.
Okay.
Huh. So if we use 70s to 30 or 80s to 20,
Okay, so if you increase the proportion of one of the constituents of your polymer, let us say you make it 70, you will obviously have to increase the other one to 30.
yeah, yes,
So that means the levels of these two factors or constituents is not independent of each other. Now, in such cases, these designs are not recommended. The designs that are recommended for such cases are called mixture experiments.
okay,
I haven't so far released the video. It's in pipeline. I have made it partly. And when I make that, I will send the links to you. We teach that sometimes if it is applicable in some cases. It's applicable in case of, let us say, I'll give you another example. Let us say you are trying to develop an alloy. There is a company called Mishra Dhatu Nigam who try to develop different alloys, or another company want to develop a new alloy for some defense application. We are into going heavily into defense, so I'm just giving that example. So let us say there are three elements in that particular alloy. There is copper, there is iron, and there is some magnesium or whatever it is. So if you increase the proportion of copper, you will have to decrease the proportion of other two elements in the alloy. That is another example of a mixture experiment, wherein the constituents or the levels of the factors are not independent of each other. So the design of experiment that we have discussed yesterday and today assumes that the factors are independent of each other. So the polymer experiment that you are describing, I would probably say that it will require a mixture experiment. Uh, may need a little more discussion, but prima facie, I feel that it's going to be a mixture experiment.
Okay. Yes. Thank you.
Yeah. Any other question? Okay. I will proceed further. And now I'll go to, I have talked about the resolution codes. So we have, yeah. So this nine factors will require this, and then something like this. So you can select the design appropriately by number of factors and resolution codes. So you can have 2 to the power k minus 2 and k minus 3 designs. What is k minus 2 design? So 2 to the power k minus 2, that means it is 2 to the power k design divided by 2 to the power 2. That means 1/4 of fraction 2 to the power k divided by 4. And it is written as 2 to the power k minus 2 because this 2 to the power 2 is in the denominator. So it's k minus 2. That means you are starting with full factorial design of k factors, and then you are looking at 1/4 fraction of that. K minus 3 will be obviously 2 to the power k minus 3 will be 1/8 fraction of the full factorial design. And you can also have, so you can, in general, you can have 2 to the power k minus p designs. 2 to the power k minus p. And this means 2 to the power k divided by 2 to the power p fraction. So these are fractional factorial designs that you can get. And these could be either 3 or 4 resolution designs. These could be useful if we need to screen only and or experiment of higher number of runs is expensive or not feasible. Now we'll see an actual experiment and do this in Minitab. And I will show you few additional features that we didn't discuss yesterday, like residuals, predicted values, etc. Now this is a experiment with in a chemical industry. A chemical engineer has identified 5 factors that may have effect on yield. These factors and labels for 2 to the power 5 minus 1 experiment are shown in the table. Create an experiment in Minitab with a single replicate. You can use Sigma Excel also or any other, but you can create this. So there are 5 factors and you are using 2 to the power 5 minus 1 design. So I go to Minitab. Now I go to Stat and I will see what confounding it shows. Stat DOE factorial, create factorial design. And now I select 5 factors. I select 5 factors. If I click on this, it is the same table that I showed you some time back. With 5 factors, you can either have 8 runs with red design, that is a full factorial is 32. So 8 means 1/4 fraction, 2 to the power 5 minus 2. 16 is half fraction, which we have to do. And that's the resolution 5 design, remember. So I'll say OK here. And in the designs, I select half fraction here. There is no center point. Number of replicates is supposed to be 1. Blocks is 1. I say OK. In factors, I need to enter the values. So I have to enter the values as per the table that is shown. Feed rate 10, 15. So I'll say this is feed rate and numeric factor 10 and higher level is 15. B is catalyst 1, 2%. So this is catalyst. And the levels are, it's a numeric factor 1%, 2%. Factor C is, maybe I can, okay, I go back here. Agitation rate 100, 120. I'll just call it agitation. Okay, I can call it agitation rate. How much was that? Sorry, 100 and 120. So this was 100 and 120 agitation rate. That's probably RPM. The fifth factor is, yeah, temperature 140, 180. So this is temperature, numeric factor 140 low and 180 high. And the last factor is, and the levels are concentration 3 and 6%. So the last factor is concentration 3 and 6, I suppose. 3 and 6%. I'm just double checking whether I did it correctly. Percent correct. Yes. So these are the factors and levels that I enter. So if you remember, we have selected a half fraction here and added the factors and levels. In the options, I can of course check randomized runs and again change the design order by a stat DOE display design and use the principal fraction. You can keep it as a principal fraction. And if I say OK, it will show you the extent of confounding that is there. So it says that fractional factorial design factors 5, base design is 5 factors, 16 runs, resolution code is 5, and runs 16, replicates 1, fraction half, and design generator is E is equal to ABCD. So ABCD is equal to plus, and in principal fraction means the identity column is plus ABCDE. So main effects are confounded with 4-factor interactions, as you can see, as per the resolution code 5, and 2-factor interactions are confounded with 3-factor interactions. So this is the confounding structure that Minitab has already given. I go back to the design. If I want to, because I want to add a column for a response here, it is customary or easy to add the response column by displaying the design in standard order so that I can copy the data from the response tables file. I suppose that should be there. So I open that response tables DOE October 18 file. I hope it is there. Chemical DOE chemical yield 5 factor 16 runs, correct. So 140, 140, 140, 180. So is it 140, 180? Yes. Then 100, 100, 120, 100, 120. Yes. 1122, 1122. Then 10, 15, 10, 15. Yeah, I think that's correct. So I can copy this yield column now from the response tables and just paste it in Minitab. So this is the actual yield when the experiment was actually conducted. With this, we are ready to analyze the data. We still have 13 minutes for the session, so I'll complete this example and then we'll close this session on fractional factorial designs. So I go to stat DOE factorial and analyze factorial design. The response is yield. Remember, friends, you can have multiple responses also, and you can optimize multiple responses. That increases a little bit of the complexity when you analyze, but otherwise it's very easily possible to do those kind of things. I have shown probably in one of the videos multiple response optimization. So yield is the response. The terms that you can see here will be only up to second order because you have chosen a resolution code 5. So main effects and 2-factor interactions only will be shown. You won't see the 3-factor and 4-factor and 5-factor interactions because they are not there in this. You cannot calculate those because the resolution code is 5. So it is okay here. Now in the graphs, I will talk about the 4-in-1. Now I am going to talk about the residuals today. In the storage, I add fits and residuals. So it will store the fitted values, that is predicted values for that row, and difference between the observed and predicted values. So it has given me a Pareto chart after analysis. So it shows that B, D, B, D, D, E are significant and rest of the are not significant at this point. Of course, effect of C is actually negligible or zero. So you can technically omit C, But if there is a interactions with C which is significant, you may not be able to omit that. Secondly, if you look at this graph, let us say I copy this and I just paste it in the in a blank sheet in. Okay, so this was the Pareto chart that I have shown you. You know, look at this lens PSE. So this is not a standard error. So if you look at the degrees of freedom, total number of runs is 16. So available degrees of freedom is 15. And effects how many? You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So you got 15 effects and 15 degrees of freedom. Each effect requires 1 degree of freedom because there are two levels. So, so the error degrees of freedom will be 0 because all are consumed. So that's why it uses an alternate method of calculating the standard deviation and makes this Pareto chart. Now this will be refined if I ask Minitab to do ignore the effects which are not significant. Yesterday I have shown you how to reduce the reduce the number of terms. But before that, if I look at Minitab now, and if I go to the table, you will see two extra columns here, fits and residuals. Fits means what is the predicted value for that. Now, since there is no degree of freedom left for error term, actually in this case, all fitted values are exactly matching with the actual observed values. So it's not going to give me any interesting information. If you look at the ANOVA table, that also will show you 0 degrees of freedom. So if you look at this analysis here, you can see here p-value star because there is no degree of freedom available for error term. So if you look at the effect, this is the ANOVA table, I'm sorry. So the error term has got 0 degrees of freedom here, and therefore the F value, F distribution and the P value of this are not calculated. But it uses some alternate method to estimate which effects are likely to be significant. Of course, it has given the regression equation for prediction. But at this stage, let us reduce the design, and for that, I will go stepwise, and I'll say backward. I'll keep the alpha risk as 0.110%, that is 90% confidence level, and I'll say okay. Now it will reduce the model, simplify the model. I will show you the Pareto chart now. What is the final Pareto chart that it has shown? No, this is the original. This is the second one. Yeah, this is the reduced model. So after reduction, it has ignored all the other things. Only B, D, D, E, BD, DEE are shown here. They are significant. If you look at the ANOVA table, then I go to the session window and go to the now new ANOVA table. Only few effects are left. So now there are 10 degrees of freedom available for error term. So you get nice p-values. All p-values are below 0.05 actually. So all effects are significant. Model summary, if you see, R square is 97.89, adjusted R square is 96.84, and predicted is also 94.6. So very good model. And then you got coded coefficients and a regression equation, and you can of course get the contour plots, etc., everything. Before that, I would like to explain the residuals because I didn't talk about the residuals yesterday. Residual plots of yield. So now there are four residual plots. If you look at the first one, this is the normal probability plot of the residuals. And I will again go back for a moment to this tip. So you have another column fits 2 and residual 2, which are for the second iteration when many of the effects were reduced. The model was reduced. So now here you can see that for the first row, for example, the predicted value is 55.875. The actual yield is 56. So the residual is 56 minus 55.875, that is 0.125. Second row, predicted fitted value is 53. Predicted value is 52.625. Residual is, so in that way you calculate all the residual values. Some residuals are high, 5.375. This is a very high residual value, while as many of the others are small. But if you this a normal probability plot of this is plotted because the assumption is that these residuals are supposed to be normally distributed with a mean value of 0. So let us look at that normal probability plot of residuals. Sorry, I chose a yes, this is the one. So normal plot of residual, this seems to be okay, and this is that high residual value, and it shows 5.375. But if it was too high, Minitab might show it as a red. But in the table, in the session window, it might show as a unusual value. So if you go back to session window, it might show you unusual values. Yes, unusual observations. That means you may check your data, typographical errors in the data or data collection once again. So observed value is 9, yield is 69, but the fitted value is 63 with the model. So the model prediction is not very well matching with the observed value. So the residual is 5.38, which is pretty large. And Minitab has shown this as a large residual and unusual observation. So you are supposed to do a double check on that one interpretation of the residuals. So this is that large residual. Uh, if you don't look at this large one, the other points seem to follow the normal distribution pretty well. The lower graph is the histogram of the residuals, which should look like normal, but usually for a low number of runs, the histogram may not be very clearly telling you what's happening. On the right side, versus fit. 0 means the predicted value. So these are the residuals, how far you are away from the predicted value for different fitted values of the yield. So if your fitted value or predicted value is 50, the residual values are +1 and -3. While as here it is a very high residual for a 65 middle value. So this seems to be something different, which is a 5 point something value, which is a high residual. Now, in this versus fits plots, what you are supposed to see is you are supposed to see. I'm just going to copy this and show you. Sorry, once again, what you should look in this graph. So I'm just going to paste it in PowerPoint. Yes. So this is versus fit. And now what you should look at is the assumption in regression is that the variance all throughout is equal. That means the residual should be generally um, fitting in parallel lines. So I will just put some two lines or equal above and below. So let us say it is between these two values. So so if you are seeing all the residual generally within a parallel band, you will say, okay, so this looks like a large residual. This is actually borderline. Minitab hasn't flagged out. So this is not a very large residual as far as Minitab. You may look at it, but they should be in a parallel band to show that variation in the data, the variance of the data of the residuals is equal all throughout. That's the assumption that you make in residuals. Abnormal residuals could be something like this, which I will show you. If you see the residual plots, let us say this is your fitted value 0. And if you see a loudspeaker pattern, that means the residuals are fitted. So this is an increasing. So this is a loudspeaker pattern. That means the variation here in the fitted values is much higher compared to the variation when you fit a lower value. The other possibility is that there could be a dumbbell shape or there could be some shape like this. That means in the middle, the residuals are more. This might tell you a non-linearity or some kind of abnormality in the model. Maybe a transformation may be required. There are different possible patterns, and you need to get used to those interpretations and see. That will require a little bit of practice of using the DOE in real life. So this is about the residuals interpretation. And of course, you can plot the remaining graphs. If you go to stat DOE and say factorial and then cube plot, of course, will be there, but there will be multiple cube plots because it will be divided into multiple. Okay, this is one, but there will be more cube plots. So you have to select which ones you want. Yeah, I think Mosumi Goswami has raised a hand. So what is the question, Mosumi? Mosumi, do you have a question? You raised hands, maybe by mistake. I So you could do this, or you could also do the contour plots like yesterday, contour plots, and create for all, generate for all pairs, and this factor which is not there. Contour plots are two factors at a time, and the factor which is not there, you could set it at the middle value, or hold values will be at middle values or high values that you can change. So you just click here and you will see the contour plots of different factors. And you can move around and see if you want to maximize the yield, the highest yield is for the darkest green portion. So that means somewhere here. So if I click here and say crosshairs, then it is here somewhere. And that is 85% yield or something. And then you could also do an optimization like the response optimizer, like we did yesterday. And maybe Yashwant had joined. I'll close the session in a minute or two. So if you go to stat DOE, the response optimizer, again, you want to maximize yield, you want to maximize. You could minimize or whatever, depending on the type of response. And then you will say, okay, the lower value that I want at least is let us say I want 75 and target is 95. That may not be possible, but whatever, let us see what it gives. So it gives me the settings of different factors, and it tells me that the predicted maximum yield that you can get is 94.87 with catalyst at 2, temperature at 180, and concentration at 3. Of course, you can change the settings by moving the red lines and see what happens if you change the settings here dynamically. So that's the way you can use Minitab to analyze this kind of fractional factorial designs. I think that takes me to the end of this session on fractional factorial designs today. So between yesterday and today, we have discussed the full factorials and fractional factorial designs. There are other types of designs, Plackett-Berman, which you can look at slide number 101 and 102, which are occasionally used. And you may look at the related videos also, which might explain this to some. There are a few more types, Latin square designs and Greco-Latin square designs and other things. So these are the things that you could do. With that, I will stop sharing and I will say that I have completed this today's lecture on fractional factorial designs. If there is a quick question I can take, otherwise I'll hand over this to, I hope Yashwant has joined.
Good evening, sir.
Good evening.
Thank you so much for a wonderful session, sir.
Most welcome.
Sir, our request is, is there any related papers on this concept, whatever you discussed in this talk?
I have
So if
given
you
complete list of
share,
videos. So there are total 12 videos that you can see. Papers will be available also. But if I find some papers, I'll pass on to Dr. Vyavhare and Vrinda madam. So I'll
yeah,
pass
if you
on
share
those.
the relevant papers, it will be
But
very
list of videos I have shared yesterday. You should get
sure,
it
sir.
from.
Definitely, we'll follow video, sir. Additionally, we request if the any other papers, then we will
You
get
can do
more
Google
idea.
search and get a lot of videos on DOE. You can just do a
Okay,
Google search.
okay, sir.
I don't think you need my help on Google search. Nowadays, you can
Yes,
get
sir. Yes, sir.
dozens of articles on DOE. But
So,
I can share if I have already downloaded some papers, I'll do that.
like your papers also, if you share, you can.
My paper on DOE may not be there. My papers were mostly on the reliability stuff. The DOE, there may be some lecture that was available, but I have already shared that through my lecture today because I
Okay,
have
sir. Okay,
done
sir.
DOE tutorial for some conferences also. They were similar. Those were
Right.
similar.
Okay, sir. Sir, one more small doubt, sir. For example, like if you take DOE or Taguchi, initially we need to for Taguchi design, like so what parameters you
I
have to
haven't
take.
discussed Taguchi designs here. No, the selection
Uh,
procedure is different. You
Not
need to
about
use
Taguchi, sir.
linear graphs on Taguchi
For
designs.
example, sir, my doubt is you are entering the data one by step by step. Finally, we got an Excel table. So can we copy and paste the entire Excel sheet, Excel data in Taguchi, not
No,
Minitab directly, sir?
please don't do that. I said I haven't covered the Taguchi designs, and the Taguchi arrays are to be used from the Taguchi designs, and selection is to be done using the linear graphs. Please do not consider this lecture as a lecture on Taguchi designs. It's a
Not Taguchi,
separate
sir.
lecture.
I'm
No, you
just
said copying and pasting in Taguchi designs. No, no
I'm
way.
asking, sir. Not
No,
Taguchi,
no,
sir.
no, don't do that. I'm answering.
Okay, sir. Okay, sir.
Don't
I'm
do that.
asking
It's
if
a
you do
different
like that,
design,
what will
and
happen? I'm asking the doubt, sir. Okay,
I
thank you, sir.
mean,
Thank you.
you will get completely messed up.
Right, sir. Right, sir.
These are called classical designs. The designs that I taught yesterday and today in the two sessions are called classical designs.
Okay,
The
sir.
Taguchi designs are similar but not same, and the
Okay, sir.
selection procedure is very different. The Taguchi created linear graphs and orthogonal arrays which have to be selected. The Minitab selection procedure is also different. You'll have to select which interactions you want and so on and so forth. So I won't, unless you know thoroughly how to select the Taguchi designs, do not enter that area.
Okay, sir. Okay, sir. Thank you,
Yeah.
sir.
Yeah.
Thank you.
We
Thank
have
you.
done a complete 2-day programs on Taguchi designs at C8 and some other companies. But this lectures, I didn't cover the Taguchi designs. No.
Thank you, sir. Thank you.
Yeah.
Yes, thank you, sir, for your such a nice and wonderful session on partial and full factorial design.
Fractional, call it fractional.
Fractional design.
Partial is usually not used.
Partial. Yes, sir. Thank you. Sir. Yes. Thank you, sir. Thank you very
Yeah.
much, sir.
So, welcome. I'll close my video and I hope Yashwant Mahakala
Yes,
joined.
sir. Yes, sir. Sir has joined. Yes, sir.
Okay,
Please
great.
Yes,
invite.
sir, I have joined. I have joined.
Okay. Okay, Yashwant, all the best to you. Carry on.
Thank you, sir.